Imagine trying to determine the exact value of a mathematical function deep inside a region, using only the information available on its outer edge. In the realm of complex analysis, the Cauchy Integral Formula makes this exact computation possible. If certain conditions are met, the data along that boundary path defines the function at the interior point. The perimeter contains all the information needed to solve for the inside. This relationship creates a bridge between the study of shapes, topology, and the study of functions, complex analysis. To find the structural origin of this connection, we can look at James Munkres' standard textbook on topology. Munkres makes a deliberate pedagogical choice. He places a heavily analytic formula directly inside a chapter dedicated to the separation of spatial planes. The placement reflects a specific mathematical reality. For a specific class of functions, the boundary values determine the interior values. Understanding the topology of the plane reveals the underlying structure of these rigid, predictable functions. We begin by establishing the physical arena, the complex plane. We define a simple closed curve, or Jordan curve. This is a continuous path that never intersects itself and terminates exactly at its starting coordinate. This curve separates the plane into two distinct regions, a finite bounded interior and an infinite exterior. This topological separation provides the required scaffolding. Without it, the functional analysis cannot take place. Within this boundary, we introduce a mathematical function. This function must be holomorphic or analytic. To be analytic, the function must be complex differentiable at every point within the domain. In standard real-valued calculus, differentiability is a common property. In complex analysis, it is a much stricter constraint, as it requires the derivative to be identical regardless of the direction from which you approach a point. If a function completely satisfies this constraint inside our closed curve, its behavior becomes mathematically locked in. This equation is the Cauchy Integral Formula, the mechanism that links the closed curve with the analytic function. On the left side, f of a is the target value at our specific interior point. The right side defines an integration path. The variable z travels along the loop gamma, meaning the calculation only occurs on the boundary. The term 1 over 2 pi I is a normalizing constant. It is derived from the topological winding number, which tracks the path's rotation around the point. The denominator, z minus a, acts as a mathematical probe. As the integral completes its circuit, this term perfectly isolates and extracts the function's value at the interior point. The equation works like a scanner, reading the perimeter to reconstruct the values inside. Since f of a is defined by an integral, we can examine how it reacts to differentiation. Because the integral is evaluated with respect to the boundary variable z, we can differentiate with respect to the interior variable a directly inside the integral sign. This leads to a significant result. If a complex function is differentiable once, the formula proves it is completely differentiable infinitely many times. We can generalize this to find the derivative of any order. This infinite differentiability shows why complex functions are more stable and interconnected than those in real number analysis. To see the formula in practice, consider this integral, e to the z over z minus 2, along a circle of radius 3. First, we identify the path. A circle of radius 3 is a simple closed loop. Next, we locate the singularity where the denominator becomes 0. At z equals 2, the point sits inside our boundary. The numerator, e to the z, is our analytic function. Applying the formula, we find the solution by multiplying 2 pi I by the function evaluated at z equals 2, giving us 2 pi I e squared. To explore more rigorous mathematical topics, like this video and subscribe to the channel.